Welcome everyone. Today we'll be looking at the lesson entitled Rational Expressions Day 1. We'll be doing several manipulations and operations with these rational expressions over the next couple days. This is the first of 2 lessons. And so what we're going to do is just define what it means to be a rational expression, try to develop some concepts around the rational expressions, and then as mentioned, we'll do some manipulations and operations with them. So why don't we go ahead and dive right in and start to talk about what it means to be a rational expression and then go from there. And so here's what I have on my paper. I'd encourage you to write this as well on yours. When I think of a rational expression, I think of it as a quotient. And by the way, quotient means division. So a quotient of 2 polynomials. Okay, you've worked with polynomials before. So what it means is we're going to have a polynomial in the numerator, polynomial in the denominator. And the way I would sort of categorize it is we must have at least degree 1 in the denominator. So go ahead and put this in place if you would. Now, rather than going ahead and putting an example right off the bat here, there are several over the course of this entire lesson, so I'm sure we will see these and be able to relate it to this definition nicely. So again, a quotient of 2 polynomials. At the end of the day, a rational expression is just a fraction. And if we get a little phobia when we hear the word fraction, don't worry at all. Even though these expressions are very abstract in nature, I'm going to try to break it down for you as concretely as I possibly can. Now the first manipulation that we're going to do with rational expressions, as it says on your sheet, is just to simplify them. And another word for simplifying when we're talking about rational expressions is just reducing. So if you remember the concept of reducing fractions, that's essentially what we are going to be doing here. So, and this is a big conceptual piece for us. So we're going to be reducing the expression so there are no, and here's the key buzzword, common factors. In fact, let's underline both of them. So no common factors in the numerator and denominator. That's how we know it's reduced. And again, you've been reducing fractions now for a while. And when your teachers asked you to reduce fractions, what you looked to see is if there are common factors in both the numerator and denominator, and by canceling out those common factors, we can reduce. And so we'll be doing that momentarily here, but there are a couple conceptual things we need to kind of figure out when dealing with rational expressions. So I have a very specific example right here, which we'll go through together, and then just a little investigation, and this one's a huge one, even though it looks very simple in nature, so we'll get to that momentarily as well. So one of the concepts that we have dealing with fractions is that there are restrictions. There is an issue when I have a fraction. And I think what I'm going to do is just sort of put in the conclusion first and then go through A, B, and C to kind of highlight that conclusion. Usually the conclusion comes after, but I think in this case, let's go ahead and develop it in a slightly different fashion and then go back and do the example itself. So long story short, if I have a fraction and I have any 2 non-zero values, so if I just take 1 on top, divide 2 on the bottom, that is a rational number. It's a fraction, right? It's division. And I do that and I get an answer. No big deal at all. The issue arises when I start to incorporate the number 0 in a very specific spot. So if I have 0 in the numerator, no big deal. When I do 0 divided by 1, 0 in the numerator is not a problem because it's going to give me an answer of 0. However, when I have 0 in the denominator, I'm going to have an issue. So as we do know, and notice I get an error message right there, we cannot divide by 0. And so there is a restriction when dealing with fractions in that the denominator can't be 0 because if the denominator is 0, then I get an expression that is not defined mathematically. And so you see that right there. In fact, again, I want to kind of put in our conclusion essentially when we talk about domain, and I'll come back to the idea of domain in just a moment, but values that make the denominator 0, excuse the shorthand here, must be excluded from the domain. So again, just with that very simple calculator work, 0 in the numerator is totally okay, but 0 in the denominator makes the value of the expression undefined. And so if we have an x value that will make the denominator 0, we need to exclude it from the domain. And coming back to the idea of domain, just in case you're not clear on what that word represents, the domain is a representation of the values that you can put in place of x, the inputs for x. And so, not to belabor the point too much here, but I look at this expression, and this is a very prototypical rational expression right here, polynomial in the numerator, polynomial in the denominator. And I look at this and I say, well, wait a minute. I have an issue if the denominator is going to be 0. And so what that would mean for me is that x can be any number, but if it was 3, I would have a problem. And so the number 3 would be excluded from the domain because it makes the denominator 0. Okay? We don't care about the numerator being 0, but we do care about the denominator being 0 because that can't produce an answer. And so any value of x that makes the denominator 0 is excluded from the domain. Okay? So conclusions in play. Now as we look at this expression over here, I look at this and I say, okay, well, if there are values of x that make the denominator 0, they need to be excluded. And we've dealt with quadratics before. So in terms of setting it to 0, I would almost do this, kind of think about it that way. And I would factor it, and just to kind of get this rolling here, it looks like -5 and -1. And you look and be like, oh, wait a minute. If x is equal to 5, that would make the denominator 0. And if x equals +1, that would also make the denominator 0. And so as a result, I'm going to go ahead, actually it's probably a good idea to do this, just on the paper there. So just throwing that in place, putting it in factored form, and then realizing, okay, what that means is x can't equal 5 and x can't equal 1. And just to be clear, just so you can separate your work from your answers, I'm going to start boxing some of these up. Probably do that all the way through. Okay, so x can't equal 5 and x can't equal 1 there. Awesome. Same idea here. So I'm looking at this and I'm thinking, well, that denominator can't be 0. And if I have a quadratic in standard form, what we probably want to do is break it down into its factors. And then once we have the factors, then I could think about what values would make them 0 and exclude them from the domain, of course. Now you can go ahead and use my method that I taught you with this, or you can just go ahead and do a little trial and error. But I'd encourage you maybe to pause the lesson for just a moment and see if you can factor this okay. Should be able to factor a quadratic with a number in front. We'll be doing that over the course of this lesson too. All right, so here's what I got. 2x and x right there. And I'm getting a 3 on this end and a 7 on this end. 14x and 3x, that looks good. I've got to combine to a -11x, so minus on the 7, plus on the 3. And then what I would do, almost, you could do this however you want, but you're basically saying, well, 2x plus 3, that can't equal 0. X minus 7, that can't equal 0, those two factors, because if they're 0, they're going to make the expression undefined. So as a result, you'd say x can't equal -3/2, or x can't equal +7. So be aware of the domain dealing with these rational expressions as we go through the process. Okay, now let's get into this simple but very, very important investigation there. This is probably the most common issue that I see with students working with rational expressions. when can you cancel terms in the numerator and denominator, and when can't you cancel terms in the numerator and denominator. So let's start with this. If I said to you, reduce 6 over 9, you would say to yourself, okay, I know that 6 is 2 times 3, 9 is 3 times 3, and yes, this is what's called a common factor, and so they cancel out, and as a result, if I asked you to reduce 6 over 9, you would tell me that's equivalent to 2/3. So the question is, can you simplify that expression by canceling out the 3's right here? And the answer is absolutely yes, because the 3's are what are called common factors. Now the question, of course, is, what if they weren't multiplication symbols? What if they were addition or, quite frankly, subtraction symbols? Can I cancel out the 3's right here? And so if you look at this expression, well, 2 plus 3 happens to be 5. 3 plus 3 happens to be 6. So that expression right here, if you were to evaluate it, really is 5/6. Is 5/6 equal to 2/3 when I cancel out those 3's right here? And the answer, of course, is no. This is not the same as its reduced form right there. And the reason is because these 3's are not common factors. The 3 is part of the overall numerator. This 3 is part of the overall denominator. It is not a common factor to the numerator nor a common factor to the denominator. So this is where we just have to be a touch careful, in terms of when can we cancel and when we can't. As I said, it's probably a situation where I see most mistakes dealing with this lesson on trying to cancel out when you can't. I know it's tempting to cancel out 3's right here, but as we see, it is not numerically equivalent to do so. So here's our conclusion. Let's put it in play and then use it over the course of some of the examples that we'll see. So terms in the numerator and denominator, and again, excuse my shorthand here. So terms in the numerator and denominator can only be canceled if they are common factors, and there's that buzzword again. Okay, so underline the two words there, common factors. So we will not try to cancel anything out until we've asked ourselves, have we factored the numerator? Have we factored the denominator? That's the key. All righty. Again, it seems like if you saw these expressions and they were just numbers, you would know absolutely when to cancel and when not to. But because they are more abstract in nature, there's this just intrinsic desire to cancel things out and make it simple when it doesn't allow us to do that. And I'll show you a perfect example of that coming up in just a moment. All right, so I always like to do this for you so you have it as reference. So some strategies. Our first manipulation, again, is just simplifying rational expressions. So here are the strategies that I would say work really well for this. So write the numerator and denominator as a product of factors. Absolutely. I don't even think about canceling stuff out until I have explicitly factored the numerator and factored the denominator. Okay. And then number 2, cancel out any common factors. There it is again, bold for you there, in the numerator and denominator. So this feeds nicely into what we've been talking about. And let's go ahead and start example 2 then. So it does say simplify each rational expression and also find all numbers that must be restricted from the domain. So we used example 1 and the investigation now to completely take care of example 2. So let's start out with this. I'm not going to try canceling until I've factored. So if you're kind of looking, ooh, I've got x squared and x cubed, I want to cancel stuff. No, 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 no. Not until you have completely factored numerator and denominator. So numerator first. It's a binomial right now. To factor it, as we've kind of talked about before with factoring, the first thing I always think of is there a greatest common factor to pull out of there? Well, it looks like I can pull out a 3 from 15 and 24, and I can also pull out an x from x squared and x. So I'm going to factor out a 3 times x, 2 factors, 3x, and then see what's remaining, and it looks like I will get 5x plus 8. Excellent. Now the denominator is kind of interesting because the denominator is what's called a monomial. It is just one term. And that one term is made up of a variety of factors. So to be honest, there are a couple ways you can view this. And if I write something on the board that it's just you're like, I don't think I need to do that, you don't necessarily need to follow this particular process. But I think of this monomial as a product of a variety of factors. You know, I could write 6 as 3 times 2. And in times, well, x cubed is really just x times x times x. So that monomial, as I said, is this truly necessary to break it down this way? No, not necessarily. But from a visual standpoint, it actually is pretty helpful. Because now what I have is a product of factors in the numerator, 3 times x times the binomial 5x plus 8. And in the denominator, I have 3 times 2 times x times x times x. Factors, factors. Now I can see what's common to the numerator and denominator, and they can cancel. So everybody, 3's can cancel. X's can cancel. And that seems to be it. And so when I reduce this, what I'm left with is 5x plus 8 as a binomial, and then 2 times x, so it should just be 2x squared. Awesome. Now again, you probably could have done a little canceling with the 3 and the x and just had it as 6x cubed, because you would have been like, oh, I know, 3 over 6 is like 1 over 2. So you would have still gotten your 2 in the bottom. X over x cubed, well, this would cancel out with one of these, and you'd still have x squared in the denominator. So you probably could have gotten this without breaking it down the way I did. Okay. Now, one thing we do have to take care of course, is the denominator. Remember, can't be 0. And so just off to the side here, I'm going to think to myself, well, I know that this can't be the case. So that 6x cubed can't be 0. So, you know, I would kind of divide by 6, still gives us 0. I'd cube root, and cube root of 0 is still 0. So at the end of the day, everybody, it looks like x can't be 0. Because 6 times 0 cubed would give me 0. So in terms of an exclusion from the domain, there we have it. Awesome. Let's move on to letter B. Now, obviously quite a bit more complicated rational expression. We have a degree 4 numerator, a degree 4 denominator. It looks pretty heavy. To reduce this rational expression, again, before we do anything, we have to think about factoring. And here's what I would say. I've been at this a long time. I've seen students do a lot of things. One of the things I would see students do is can't resist the temptation. So you have a 4x to the 4th on top, you have a 4x to the 4th on bottom, and I know you want to cancel those out. But these are not factors of the numerator and denominator. Again, they are separated by addition. They are part of the overall numerator and part of the overall denominator. They are not a factor of each. So you cannot cancel the 4x to the 4th. Okay, so if it's separated by addition, you're not going to be able to cancel it because it's not a common factor. Okay, but I'm going to get this going here. So first and foremost, I look for a GCF. It just so happens I can take out a 2x squared. And when I do, I would get a 2x squared there. Looks like I get a plus x, and looks like I get minus 3. Hope you don't mind me jumping the gun on that. Denominator, same idea. I can take out a 2x. And I'll get a 2x squared plus 13x plus 15. Awesome. Now, I took out the greatest common factor. That's great. Now what I need to do is try to go further. Again, you're always looking at your expression and can I break it down further? Now it just so happens you can break both of these down, quadratic trinomials. So you feel free to use my method that I taught you, or a little trial and error, or any other method for that matter. But I'd encourage you to pause the lesson for a moment, and let's go ahead and factor both those quadratic trinomials. Okay, so when I factored them, again, two binomials, of course. The numerator, I got 2x plus 3 and x minus 1. And in the denominator, again, don't forget your 2x's. Those are part of the original expressions. And I got 2x plus 3 and x plus 5. Okay, hopefully you did too. Now do you notice the difference here? Factored form, standard form. Can't cancel anything in standard form, but now that everything is a product of factors, we can start to go to town on this. Factors of 2, they're gone. Factors of x, they're gone. Binomial factors of 2x plus 3, they're gone. And notice, each one of these is truly separated by multiplication, and so that's why they are considered factors of the numerator and denominator, and hence can go. So everybody, here's your answer. Box it. Now, here's where we're going to be just a touch careful. So remember, and here's what I'd encourage you to do, is just very, very lightly on your paper. I can't do it lightly, so it's not going to have the same impact, but very lightly circle the denominator. That's what can't be 0. And then what I want you to do, almost in the same breath, is come over to the factored form of the denominator and very lightly circle that. That's what can't be 0. So even though we simplified this and you're thinking to yourself, okay, very easy, x can't be negative 5, there is more to it because this is really only the simplified version of the original. And what we're looking for is the domain of the original. And the original is made up of these factors here. So as a result, we look at the variable factors. Again, the 2 is not going to do anything, but we look at the x, we look at the 2x plus 3, we look at the x plus 5. Those are what can't be 0. And if you use the 2, sometimes I see students do this, something like that. Again, you can avoid that too. But you get that, and you get that. So in terms of the exclusions, it's not the simplified version that you look at, it's the factored form of the original version. And so as a result, divide by 2, so now I know x can't be 0. Subtract the 3, divide by 2, x can't be negative 3/2, and lastly, x can't be negative 5. Okay, so please don't forget about your exclusions coming from the factored form of the original. Okay, guys, that's the manipulation of simplifying a rational expression. It leads very nicely into multiplying and dividing rational expressions. So again, just for your convenience, I just wrote some strategies there on your paper, but notice what it comes down to, everybody. For multiplying and dividing, it's all based on factoring the parts. Factor the numerator and denominator. Cancel out common factors, and then multiply across. This is exactly what you learned when you just started work with fractions. Nothing different. It's just the expressions themselves are a little more complicated to work with. So let's do example 3. And notice now we're getting into the operation of multiplication here. And it says perform the operation with the rational expressions. And also notice, find all numbers that must be restricted from the domain. Okay, so here's what I need you to do on your paper. Again, I'm going to pretend to do it. You're going to actually do it because I can't do it lightly and I just don't want it to get in the way of my work. But very lightly, we know in this individual fraction the denominator can't be 0. So would you do me a favor, just very lightly circle that denominator. And in this individual fraction over here, I know that this denominator can't be 0. So if you would, just very lightly circle that denominator. I think that'll be helpful. Okay, I'm just going to follow my strategies here. What I do very simply, is I'm going to rewrite each of these parts, numerators and denominators, in factored form. So I'm not going to build up. You talk a lot about that in with these manipulations. We're not building up the expressions. We're going to try to break down the expressions before performing the operation. So you're not like, ooh, polynomial distribution and making a 4x to the fourth and all that. No, no, no. So we're going to make it simple. All right. So to do that, we are going to factor. And just to get everything going, I'm going to factor for you. That would be x minus 1, x minus 1. Pull out an x from here. This would be x and x squared plus 1. This one, I'd pull out the 4 and get x squared plus 1. And lastly, difference of two squares, x plus 1, x minus 1. I know you can kind of factor those as I've done here. Now notice, everything is separated by multiplication. This times this times this times this. Denominator also, this times this times this times this. Because everything is factored form, and because we do have multiplication, which allows us to cross-cancel, we can go ahead and eliminate anything that is in the numerator that is also in the denominator. So for example, x minus 1 there and x minus 1 there. Absolutely can go. X squared plus 1 here, x squared plus 1 here. Absolutely can go. If I had a common factor in the numerator and denominator of the same fraction, of course they can cancel. That's what we just did. So anything in the numerator that is a common factor to the denominator can cancel out. And so as a result, now I can just push over what is remaining. I have the 4 and the factor of x minus 1. And then down in the denominator, I had a factor of x and a factor of x plus 1. Okay, so multiplication, break it down, cancel common factors, and push everything across. Now again, what did we do in terms of the denominators not being equal to 0? Well, here they are, and this is what I would do. Just again on your paper, I would lightly circle. Those are the ones, because these are the factored versions of the original denominators. So the way I would kind of think about it is x can't be 0, x squared plus 1 can't be 0, x plus 1 can't be 0, and x minus 1 can't be 0. And as a result, x can't be 0. Now this is a good one, because if I bring over the negative 1 there, or bring over the 1 and make it negative 1 on that side, square root, if I square root both sides, I get square root of negative 1. Is that going to be a real number? No, no. So in reality, this doesn't produce any exclusions, because what would make it 0 is imaginary and not real. But it looks like negative 1 from here and positive 1 from here. There you have it. Okay. And by the way, if you needed to, I'll just kind of write that there for your convenience. Subtract 1 on both sides. Here we would add 1 on both sides. Okay. Let's get into just this question right here before we do the division. So we simplified, we multiplied. Now we're going to take care of the division. So if you remember, again, just from your previous work with fractions, very simply, what do you have to remember to do when you divide rational expressions? So we change to multiplication and flip the second rational expression. So the idea is dividing by a fraction is the same as multiplying by the reciprocal. So change to multiplication, flip this to its reciprocal. The one that maybe you remember from middle school is copy dot flip. So you copy the first, change that to a dot for multiplication. So copy, dot, and then flip. Okay? So we leave the first rational expression alone, change that to multiplication, and we flip this second rational expression. So here's what we have to be careful of in this one. So this one, put a little asterisk somewhere around here, the find all numbers that must be restricted from the domain, because division is a little bit harder. So let's go through it. First of all, what I need you to do in this individual fraction, I know the denominator can't be 0. Can you very lightly circle that for me? Okay. Also in this individual fraction, I know the denominator can't be 0. Can you circle that for me? And here's the one added piece to the puzzle. When I divide, the whole idea, everybody, is I can't divide by 0. That was from the very beginning of the lesson. Can't divide by 0. Well, the problem is if the numerator over here is 0, well, 0 divided by anything is still 0. So that would make this whole thing 0, and I can't divide by 0. So long story short, everybody, very lightly circle the top right too. Because if this is 0, it's going to make this division of a whole number 0, and I can't do that. Okay, so we'll come back to that exclusion. 3 parts, not just 2 parts. Okay, but I'm going to do my copy dot flip, and as a matter of fact, well, actually, you know what? Second thought. I am going to copy dot flip initially just so you can see it. Then we'll write it in factored form. Okay, so that's what we do. That's what it means, copy dot flip. Now, of course, we get back to the same premise of example 3. And everybody, it's just a matter of factoring each part and breaking it down based on common factors. So I'm going to go ahead and factor. You can maybe be a little faster than me, or maybe you can pause the video and see if you can factor these. But this is just a linear binomial, so that just will be prime. This is a difference of 2 squares, x plus 2x minus 2. Ooh, good one on top here. Difference of 2 cubes. Don't forget this. This is coming up again and again and again. So if you have forgotten that particular pattern, if you could please refresh your memory on that, especially that middle term right here. Remember to get that middle term. You take these 2 guys and you multiply them together, x times 2. There's the 2x. If that's minus, that's plus. And then lastly, down here, looks like x minus 4, and how about x plus 3? Now notice, I wrote the numerators as products of factors, the denominators as products of factors. So anything at all is fair game that is in the numerator and also in the denominator. Again, if it was one on top of the other, we can do that as well. Here we are going to cross-cancel the x plus 3s. We're going to cross-cancel the x minus 2s. And again, if, say, for example, you had an x plus 2 on the top of the same fraction, yes, of course they can go if they are common factors. Anything in the numerator and denominator. Okay, so now just pushing it across, and I'm going to write my answer up here. You can find a spot for it if you want somewhere. So x squared plus 2x plus 4, and then what's that over there? It looks like x plus 2 and x minus 4. Box that up. That looks fantastic. Now, exclusions. So remember, and remember I had you circle, but I had you circle this part too. So all of those we have to take care of. So that would be this, that would be this, and it would be that as well. So 3 parts there. And so think about where your exclusions are coming from and what would be those exclusions as a result. So x can't be negative 2 because of that factor right there. X can't be positive 2 because of that factor right there. Moving up here, another x minus 2. We already took care of that. Now, I'll just tell you for this one, if you tried to set this to 0 and solve, it's unpleasant, but we can do it. But you end up getting imaginary numbers. So this does not produce any exclusions. But this one does. and this one does. So if I set those to 0 and see what they would produce, those are the values that we need to be excluded from the domain. Awesome. Let's move into the last piece. So we multiplied and divided today, along with the reducing part, the simplification. Tomorrow we're going to add and subtract. Adding and subtracting is an entirely different process. So we are going to completely have to compartmentalize what we did today with what we're going to do tomorrow. So I just want to be very clear on that. Now you've worked with fractions before, so the good news is we're going to use that basis to ramp it up with these very abstract expressions. But we want to be very clear on what to do when you multiply and divide, and then what to do when you add and subtract, because they are entirely different. Okay, well what do we need to add and subtract fractions? As you do know, you need a common denominator. Okay, that's totally different than the multiplication and division operations. So in order to find a common denominator, we're going to do a couple things. I'm going to show you a numerical way to pull this off, and then we'll go from there. So break down each term into a product of prime factors. Work left to right. Don't take redundant factors. Okay. Now first and foremost, I like to start out concretely with these. So you can see like, oh, this is what I do with numbers. This is what I'm going to do with more abstract expressions. So if I said to you, tell me what is the lowest number possible that 6 and 8 divide evenly into. So not a factor, but multiple. So multiples of 6 would be 6 and 12 and 18 and 24, et cetera, et cetera. And multiples, of 8 would be 8 and 16 and 24 and 32, et cetera, et cetera. And so if I asked you what is the smallest number that these evenly divide into, I'm hoping you would tell me it's 24. And I'm just going to write that there. That's going to be our answer. I'm going to show you how to get that using this process. So what we're going to do is break 6 down into its prime factors, prime numbers. And 6, of course, is just 3 times 2. I'm going to break 8 down into its prime factors. Now, as a matter of fact, I could write it as 2 times 4, but the 4 would break down a little further into 2 times 2. So you need to go prime in this particular case. And watch what happens here. It says work left to right. Don't take any redundants. So we're going to take them all, except we're going to loop the redundants. And I'm going to show you how this works. So everybody, take the 3. Awesome. Now do you see this 2? If there is a 2 in the other list, we're going to loop it. And we're going to only take it once. Okay? So again, this 2 is the exact same as that 2. And so I loop them together as a common factor. And so I take that common factor once. Now I do have extra 2's in this list, so I need that from that list. And again, anything that is intrinsic to the number itself, we need to take. So the only one that was common, meaning it was in both lists, was this 2 right here. So we took that one just once. Awesome. Hey, look, what is 3 times 2 times 2 times 2? 24. Now, if I actually took all of the factors instead of taking it just this common one once, so if I had an extra 2 right here, that would make this 48 instead of 24. Now 48 is a multiple of 6 times 8. But is it the least common multiple of 6 and 8? No. Okay, so by looping it together and just taking it once, we get the lowest common multiple. All right, here's how it works over here. And again, we're going to pick it up in next lesson, so don't panic if there's a little bit of a struggle with it. So if I factor that one, it's that. If I factor that one, it's that. Cool. I'm going to loop. That x plus 1 is common. So let's loop that. So I get x plus 1 and then x minus 1, and then x plus 1. So I took this one right here, which is the same as that. So I took the common one just once. I took that one as it was part of this list, and then I took that one, part of this one. Now, you can write this a couple different ways. If you really wanted to, this would be x plus 1 squared times x minus 1. Let's do it on this last one over here. You break it down. And so this is just x plus 3, x plus 2. If I factor this one, this is just 3, x plus 2, x minus 2. What would be great is for you to take a moment and come up with the least common multiple based on what I just factored there. All right, let's see how you did. So the first thing I would do is I would loop the x plus 2's, and now I would just take everything. So there's the x plus 3. There's the common x plus 2. There's the 3. And there's the x minus 2. There you go. Again, everybody, you're not going to worry about this too much. Focus on the simplifying and multiplying and dividing for now. We'll pick up the addition and subtraction using these multiples in tomorrow's lesson. Thanks, everybody. Appreciate it.